All attendees are on mute by default. Please use unmute button or unmute me option from the participant menu. If you have a question, please direct them to Kishore Gorti using the chat option. We will share them with the speaker towards the end of the session based on availability of time. With that, I would like to hand over to the host of today's event, Aviral Srivastava. Aviral, over to you.
Hey, thank you, Kishore. A very good morning and afternoon to all of you. Welcome to Infosys QA Roundtable 2020. It's hosted by IVS, which is the Testing Services and Quality Engineering Division at NFI. Objective of these roundtables is to get academia and industry experts together and talk about latest technology trends that are and will impact businesses and how QA organization can help improve the business outcomes. In our keynote session, Dr. Jim will talk about key aspects to ensure that an AI-led digital enterprise is robust and safe. Dr. Jim is a professor and chair of computational media at University of California, Santa Cruz. He is considered as the father of web DAP protocol. Second session will be on explainable AI. Today, deep learning networks are a big black box and do not provide explanation for business decisions it makes. This has a huge impact on business outcomes, especially when 80% of machine learning implementation that exists today will be transformed into deep learning models over next 3 to 4 years. In this session, we'll talk about applying formal methods to analyze and verify neural network. Session will be presented by Dr. Karina Passarino. She is a ACM Distinguished Scientist and working at NASA Ames Research Center through KBR. She's an ex-professor at Carnegie Mellon University. She is joined with Divya Gopinath, who works in a team at NASA Ames Research Center. Divya has a PhD from the University of Texas at Austin and pursued postdoctoral research at Carnegie Mellon University. Next, we have a session on how deep learning solutions are being leveraged to change business outcomes. We have Raji Ganesan, who is AVP at Infosys NIA division. She'll be sharing her experience on the implementation of deep learning solutions and QA challenges faced during these implementations. In the final session, we'll talk about how AI and ML is being leveraged to build QA tools of future that make lifecycle predictive, intelligent, and efficient. This session will be presented by Harleen Bedi, Senior Industry Principal at Infosys IVS Practice. She leads the team at Infosys to build these tools and work with customers to improve their journeys. With that, I'll hand over to Jim. Hi, Jim. Over to you.
Thank you. So during my presentation, I'm going to be giving pointers to a large number of other websites and also publications. To make life easy for you, I have asked Kishore if he might take a set of links that I prepared ahead of time and share it with everyone in the chat session, if that's possible. So, all right. So in my talk today, I want to go over a number of issues that people run into when they're trying to take artificial intelligence solutions, either AI solutions that are an entire system or a subsystem and part of a larger system, and how do you make them more robust and more safe for application in the broader world. So as Aviral mentioned, I'm a professor of computational media at the University of California, Santa Cruz. And then I have also recently been working as a chief consulting scientist for a AI-led web application testing startup called Autonomic, located in San Jose. Within my group, we've been doing a number of AI-related projects in recent years. I guess historically, one that I've worked on is using machine learning classification to predict where bugs are going to appear inside large repositories of software and be able to predict which changes being committed to those repositories will have bugs in them in the future. I also have a student who's been using neural network techniques in the last 2 years to be able to generate new music that meets a particular kind of sentiment. So if you want to generate upbeat music or downbeat music, are you able to not only generate good sounding music, but music that meets that particular emotional goal? And then finally, I've also been interested in autonomous vehicles. And I have a group where we've been developing a simulation technology or a simulation environment which we call Cruiseway, that's capable of generating a wide range of scenarios for testing autonomous vehicles. And so these different projects give me different kinds of insight into the sorts of things you need to do to make AI robust and safe. I think it's important to mention as we get going, we tend to use the term AI as if it is this one single monolithic thing. But AI itself is a very broad set of technologies, all of which are maybe unified by a single overarching aspirational goal to the creation of machine intelligence, but they adopt many different approaches. So we have classical machine learning, we have approaches that use neural networks. Some of them are focused more on images, others are focused more on language and language generation. And then what tends to get forgotten in modern uses of the word artificial intelligence are planner-based approaches where you're trying to craft intelligent actions through a very large space of possible actions. And these techniques are still incredibly useful as well. So it's important to realize there is no one AI, there's sort of a lot of AIs. And even though we'll be focusing on a couple broad themes in this talk, it's important to realize that each one of these different areas of AI has its own traditions and own approaches that you would need to use in order to determine safety and robustness and freedom from error. So one question is, what does AI actually look like? And so I thought it would be useful to provide a few pictures of examples of like actual AI systems just to ground our thinking and to give us a few examples to think about. Whenever I am preparing slides, I often will go to Google image search and I'll just type in whatever the thing is I'm looking for. And so in this case, I went to Google image search, I typed in artificial intelligence, and here are a range of the images that came back. And so from these, I can determine a few things. First of all, artificial intelligence is blue. And when it's not blue, it's kind of this like off orangish pink. And it somehow involves like glowing blue printed circuit trace like things. And sometimes it looks like a brain, but not always. Well, okay, I'm not sure. Maybe AI doesn't really exactly look like that. What does AI actually look like? Well, here are some examples. We have with the plants, this is a picture from Plenty, which is a vertical farming startup located in San Francisco. It may look like all they're doing is growing things, but in fact, there's a very sophisticated AI subsystem that is driving the robotics that turns on the lights, determines the frequency spectrum of the lights, determines when nutrients are fed to the plants, and then when it's time to harvest, there's a very sophisticated conveyor belt system that will then carry those plants into a separate room where they're harvested. We then have more familiar kinds of AI, like say Alexa or Siri or Google Voice, where you're able to give natural language commands and get responses back. AI can also be hidden underneath user interfaces that don't look particularly like their AI. So there's a user interface from Spotify and things like based on your recent listening. Well, there's very sophisticated artificial intelligence algorithms underneath the hood that are able to determine like, okay, what are some other songs that are most similar to the ones that you've seen before? And of course, in the middle, this is one of my favorite historical pictures of what autonomous vehicles and autonomous driving might look like in the future. Okay, so when you are developing an AI system, there's sort of an idealized AI lifecycle that you go through. So you start off with continuous gathering of data. You then use that data to train high fidelity AI models. You then perform some kind of QA testing of that model. Once the model seems like it's working pretty well, you then go ahead and deploy that model out into your real world use situation. And then you have to update those models and continually perform QA on those models as you go along. Every single one of these areas provides opportunities for errors and problems to creep in. And every one of these phases is an area where you need to be focused on how do you either avoid bias or how do you ensure robustness of the outputs from that particular phase. And so this leads to 4 QA challenges for AI. There's many others, but I'll focus on these 4 in the talk here today. So 1, understanding, encountering bias in your data sets. Like a lot of computer science, if you have bad data coming in, you'll have bad data going out. Working and dealing with bias and error in the trained AI models themselves. Dealing with mismatch between the training environment and the execution environment, and in particular, dealing with the long tail of just wonderfully weird stuff that can happen in the real world. And then finally, the use of synthetic data generation. Okay, so let's hop into data set bias. So one of the more familiar examples of data set bias is the data sets of facial images or images of people that are then used in training neural networks in order to do facial recognition. And there was a recognition a few years ago that these data sets that are currently out there and that are widely used for training facial recognition are quite biased. So here's, I'm going to present 2 tables from a recent paper called Diversity in Faces. It goes into the just how biased are these data sets. Gender and skin color and type. And you can see that there's a very strong bias in this, not just one, but many, many different widely used image data sets. There's a bias towards male images predominantly, and a super strong bias towards lighter skin colors as opposed to darker skin colors. And so as you might imagine, it's going to be, much, much harder to make a highly robust facial classification system or facial recognition system when you're looking for darker skins as opposed to lighter skins because your data set is just so biased. In a similar vein, here is the range of age groups in all of these data sets. And you can see, especially, there's almost no images of infants, very, very young infants. And then, once you start getting to, kind of child age 4 to 12, okay, it starts picking up, but there's, definitely the majority of the images are of people who are young adults and adults. And then it kind of trails off as you get older and older as well. And so, as you might imagine, well, if you were trying to do facial recognition for babies, this data set just is not going to work especially well for you. And certainly this is a hard challenge. Those of you who have kids or relatives with kids, I certainly find that even looking back at pictures of my own kids from 10, 15 years ago when they were very, very young, it could be hard to pick out who was who. And so anyway, young babies are a very difficult challenge, and you need to have good data if that is what you are wanting to do. Okay, so how can you address this kind of bias? Well, I think the key to addressing bias in facial recognition data sets or any data set altogether is you just have to understand what are the frequency distributions in your data set. And you also need to have ways of making sure that the data that you collect is highly representative in the first place. So it's a combination of having good techniques for bringing that data in the first place, and then you have to go through and you just have to study your data set before you do any training with it whatsoever. Understand your data set and understand the kinds of frequency distributions and the biases that are in there. So this Diversity in Faces project did just that. So they started with images from this large data set from Flickr, primarily in Yahoo, over 100 million images. And then they went through and kind of started working through those images and gathered images, tried to ensure that there was good diversity of the images across many different categories. But then importantly, after a really rigorous ingest phase, they also then did a lot of work to understand the frequency distributions across all of these images. Okay, so once you have your data set, you can then go ahead and train your model. But very often it's the case that even with neural networks, even with highly sophisticated AI systems, there are going to be sources of error in those models. So I'm going to talk a little bit here about digit recognition and use this very famous data set called MNIST MNIST is a data set of handwritten digits, and the problem or the challenge that you have is, given a handwritten digit, you'd like to be able to understand like what the number is that they were trying to represent. Okay, MNIST is a problem that's been studied for a long time and is very typically used in textbooks that are trying to teach about machine learning and about classification and especially about neural networks. There's one here on the slides that I recommend. It's a great introduction to neural networks. But even the very, very best of a long line of research, it can only get, 9,979 out of 10,000 of these images correct. Why, with years of study and all sorts of effort, why is it not possible to get to perfection? And why is it not possible to get these all the way correct? Well, here on the slide are the images of those 21, the ones that were not able to be correctly classified. And I think by looking at this data, you start getting the sense of like, oh, yeah, like it would be really hard even for a human. Like some of these are just plain ambiguous. They're just poorly drawn figures. And so it's no wonder that the machine learning algorithm is having trouble classifying these. A human would have trouble classifying these as well. So how might you be able to tell this? Well, one approach is to use visualization of your data set. There's a great website, link is down below, where they go through and they do interactive visualizations of many different kinds of this MNIST data set and of how it's being classified. One of the more sophisticated approaches is this one called TSNE. And essentially what it tries to do is each one of these colors is a different digit, and I've written the digit next to each one. And you can get a sense from this, first of all, like, yeah, all the similar digits are pretty tightly clustered together, but within each cluster of digits, you start seeing a different color or a number of dots of different colors. And what that's showing is that for those particular digits, they tend to have qualities that are much more similar to, a 1 rather than whatever data set or data number that they actually are. So those end up representing the cases that are just plain going to be hard to classify because, you want to get it right, but they have all the properties from another class, even though they're being clustered and clumped together with a different class. So these visualization approaches can give you really good and deep insight into like what's actually going on in your data. And it allows you to understand, get some insight into, well, how is that classification algorithm working and what might be some of the challenges that you're running into. Of course, this is just an entry point into explainable AI and into some of the discussions that we'll be getting in the next panel. So visualization is just one of many techniques for trying to explain what's going on inside an AI subsystem. And there's this entire whole subfield of explainable AI, whose entire goal is to try and give explanations to both the developers, the testers, as well as the operators of AI subsystems as to what is actually going on underneath the hood. Part of that's about trying to understand the models and what's going on inside those models. Other times it can be things like, to an operator, trying to explain to that operator at a high level what's going on or why a system is behaving in a particular way, and trying to bring some of the task context into that so that they are not getting flooded with information, but only kind of very specific information about what's actually going on at that moment. And so at the bottom of the slide there's a pointer off to a recent survey of explainable AI techniques that is very approachable. Okay. So you have your AI model, you've gone ahead and deployed it out into the real world. A very common situation that can occur are these mismatches between what you've actually trained on and what actually exists out in the real world. So I'm going to kind of borrow a problem that I learned about from Andrej Karpathy, who is an engineer working on autonomous vehicles. He just recently gave a talk about AI for self-driving. And one of the problems that he talked about in this presentation, the link is on the slides, is this problem of stop sign detection. Now, at face value, stop sign detection might seem like a problem that should be very, very easy for machine vision to tackle. The stop signs themselves have a very regular shape. They have a very predictable color, red. And the lettering on them is also very predictable. And we also generally know about where to find them because they're generally at about the height of a person, and they're generally mounted on poles. So it should be pretty easy to go ahead and find them. And indeed, for stop signs that are reasonably well lit and have all those properties, yeah, it's pretty easy for machine learning to find those. But is it the case that all stop signs are like that? Well, it turns out some stop signs are not red, they're yellow. And then sometimes stop signs are not all the way up, sometimes they're down, down way low. There are some stop signs that are circular and not octagonal, although they are red and they do have the lettering stop. And then to make life even worse, there are some stop signs that have sort of conditional logic applied to them, that in fact, it's not enough just to detect the stop sign to know what to do. You have to detect a stop sign and you have to detect the conditional logic stop sign that's there. And of course, you may be doing testing, even real world testing in a particular situation, and just not run into these. I'm pretty sure that there are none of these stop except for right turn signs in California. I think these are only, at least in the United States, back in the eastern part of the country. So there's this really, really, really long tail of like just wonderfully weird stuff that exists out in the real world. And even though you've done an excellent job inside the lab of doing your training of the algorithm, because of this long tail, you're just going to be running into problems in the real world when you run into these wonderfully weird situations. So part of the challenge in making robust AI is you have to embrace the fact that the real world has these long tails, and you have to seek them out and find them. And in fact, if you haven't found those long tails, you should be nervous because they do exist. You just haven't found them yet. All right. So one approach for addressing the long tail is synthetic data generation. So, if you were trying to look for all of the weird and wonderfully weird stop signs in the world, you might have this problem that if you're doing all of your training data in a training or your real world testing, in a small number of cities, well, those cities just may not have certain examples from that long tail. One approach for getting around this problem is the ability to have synthetic data set generation, where you synthetically create the data that you need, and you can simulate this long tail. Now, you have to know it exists and know the properties of it to be able to simulate it, but very often it's the case there are data sets that kind of have examples of a lot of these weird situations in them already. So Waymo is, in the area of autonomous vehicles, probably the company that's furthest ahead in terms of using this kind of synthetic data approach. They've done a tremendous amount of real-world testing. They've driven their cars over 10 million miles, and this is data from 2 years ago. It's very possible it's much, much higher at this point. And that's a big number, but they've driven even more. They've driven over 10 billion miles in simulation. And so this points to many of the benefits of this simulation or synthetic data approach. So even though you can get a lot of data and should do a lot of testing in the real world, simulated data can do this at much, much greater scale, many orders of magnitude more. And again, real world driving, many miles are fairly plain and uneventful. If you want to be generating rare events, well, you need to do those in simulation. And so simulation can just generate, rare events over and over again very frequently. And so the rare becomes very frequent inside simulation. There's a number of different approaches that you can use for synthetic data generation. So capture replay is a very common one. You have some data that you capture from the real world. Maybe it's a rare situation, or in autonomous vehicles, these are often near miss situations or actual hit situations that the driver inside the car who's overseeing the autonomous vehicle, they can press a button and record the last 30 seconds and then replay that. Sometimes there are data sets of real world situations. In the area of autonomous vehicles, they're what they call naturalistic driving studies. And you can get these data sets that have huge amounts of data of cars driving on freeways and in cities and so on. And it's then possible to extract scenarios, testing scenarios out of that naturalistic data. It's also possible to take that same kind of data, but then instead of kind of creating exact scenarios, you just end up extracting behaviors. And so maybe you create like a dumbed down ego vehicle or autonomous vehicle, and put those in and create testing scenarios with those. And then the testing scenarios end up coming out sort of through emergent behavior, through the actions of all these autonomous agents interacting with each other inside a testing environment. And then finally, if you're testing, say, a vision algorithm, it's possible to create synthetic data by, training generation algorithms on real-world data. So one example where this happens is in machine vision for like people's bedrooms or houses. There aren't a lot of good data sets of pictures inside people's apartments and bedrooms. People feel that that's kind of creepy and invasive. So what you do is you have procedural content generation create simulated bedrooms and dining rooms and living rooms and so on, placing furniture, usually models that come from actual manufacturers, and then you're able to use that to train your machine vision algorithms based on that. I guess one of my favorite examples of synthetic data generation is this website where they've trained these very high resolution GANs, generative adversarial networks, on faces, and then they're able to reproduce and recreate very high quality faces from that. So even though all these people look remarkably real, none of these people exist. All of these faces are generated using these generative adversarial networks. Perhaps the easiest way to figure out that they are in fact simulated, the kind of sort of shaded man who's in the upper right-hand corner, if you look very carefully at the edges of his eyes, you'll see like a glasses artifact there. He's not wearing glasses, but there's an artifact that looks like he's wearing glasses. So that's one key there. And I think actually the glasses on the woman in the upper left, I think her face looks a little off as well at the edges of those glasses. So there are these artifacts that can let you tell, but in general, you can see that these synthetic images are extremely high quality and certainly could be used for training machine vision algorithms. All right, well, let me summarize. So the first point, well, make sure you understand your training data, understand its biases. If you're not computing and taking a look at the frequency distributions of your data, you're just going to run into problems because you just don't understand what's going on. Understand why your models are making the mistakes that they do. So, don't just stop at the table telling you, your accuracies and false positives and false negatives. Like really dig in and really try and figure out like what's going on as to why these things are not being classified correctly. What really is going on inside that machine learning algorithm. You're just not going to be able to fix any AI bugs until you really have a good understanding of what's going on. Once you get that out there, the real world has this long tail. So make sure you understand that long tail and feel very nervous if you haven't encountered that long tail yet. And then finally, how can you bring that long tail back in and use it for regression testing and to make sure that things continue to be robust? Well, simulation-based testing is a great approach for doing that, or the generation of synthetic data. All right, with that, that's the end of my talk. Thank you very much. This has been Jim Whitehead lecturing at home.
Hello, everybody. Thank you very much for inviting me and Divya. It is an honor and a pleasure to give this presentation. So today I will talk about some of the projects that we have at NASA Ames, and they are related to understanding and feature extraction and input transformations with the goal of learning to do tasks by considering labeled examples. They can represent highly complex nonlinear relationships. And for our talk, we will consider networks that rectified linear units or ReLU activations that will compare the output of a neuron with a threshold value and, for example, 0, and forward that value moving forward. Next slide, please. So, of course, neural networks have found many applications. They can be used in pattern analysis, image classification, sentiment analysis, speech and audio recognition, but they can also be used and they are increasingly used in safety and security critical domains, such as medical diagnosis or perception modules in self-driving cars. Next slide. And with this increased use come also many challenges. And I'm listing a few here. So one is lack of explainability, and Jim already talked about it. So basically, it is not well understood why a network gives a particular output. And if the reason it gives an output is wrong, that might introduce vulnerabilities, bias, or simply wrong results in the network. Then there is also a lack of robustness. So for instance, small changes to an input lead to misclassifications. So this has been observed that even for highly trained, highly accurate networks, this happens. Now, our work at NASA Ames is concerned with trying to apply formal methods and rigorous testing techniques, but they are met with serious scalability challenges for neural networks because they are very large, they are highly interconnected structures, they often have huge input spaces, and these characteristics make verification and thorough testing particularly hard. And I'm adding another challenge, which is less studied, but was also a focus of our research, which is lack of intent. So, for instance, safety critical systems at NASA these are developed in a top-down manner, starting with rigorous requirements and then prototypes, and then there is development and rigorous traceability between all these artifacts. But neural networks perform particularly well in domains where we don't have high-level specifications. So they learn from examples without knowing in the end what is the logical requirement for recognizing, for example, street signs, as Jim said, or cats versus dogs, and so on. Next slide, please. So at NASA Ames, we have a project called SAFE-DNN, Safety of Deep Neural Networks, where we try to address these challenges, and we explore techniques and tools to ensure that systems that use deep neural networks are safe, robust, and interpretable. And we have several research directions. For example, we explore symbolic execution for DNN analysis. We explore parallel and compositional approaches to improve verification of neural networks. This is in collaboration with Stanford University. And we also have performed work on property inference and automated program repair, probabilistic reasoning for neural networks, and also a most recent project which develops system-level explanation using Semantic. And the overall goal is to provide strong guarantees with respect to safety and robustness of neural networks. In particular, at NASA, we are interested in using them for autonomy. And we also want to obtain compact formal explanations of neural network behavior, and this will become clearer later in this presentation. And ultimately, we want to improve testing, debugging, and maintenance for neural network. And I provided here the link to our project. So thank you, next slide. So in this for the rest of the presentation, we will focus on our projects that are related to explainability. So, and in particular, we have a paper that will appear at CVPR, which is a computer vision conference, which is on programmatic and semantic approach to explaining and debugging neural network-based object detectors. And this technique is based partially on another technique that we developed, which is about property inference for deep neural networks. And Divya will explain the details of that technique. So if you go to the next slide, please. So just to give a short summary of our latest results that will go to CVPR, and I think this is also, again, linking well with Jim's presentation. So in this work, we were interested in analyzing a detection module that is used, for instance, in an autonomous car. And this module takes in inputs, images of road images that contain street signs, other cars, obstacles, and so on. And then it outputs a bounding box around those obstacles, and those bounded boxes are used by the controller of the autonomous car to, avoid them, for instance. And then the goal of our work was to try to, the key idea of this work was to try to extract high-level explanations in the form of rules that are understandable to humans that explain the correct behavior and also the misbehavior of the detection module. And of course, the application is that you want to understand when the detection module performs poorly, because otherwise it can lead to accidents and loss of life and other catastrophic events. But also we want to understand the situation where the detection module performs well, to make sure that it uses the expected features in the image. So, for example, that its decisions are not because of the particular color of the sky, but indeed because it detected and it correctly placed a bounded box around obstacles. And in this work, we used Cynic, which is a probabilistic language to encode distributions over scenes that describe images that are input to the detection module, and then investigated different techniques to refine these Cynic programs in such a way that the probability of correct detection or incorrect detection increases. So these refined programs then can be analyzed by developers to determine if the decisions are correct, or if they are incorrect, to generate more inputs for retraining and so on. So now I let Divya continue, please.
Hello, everyone. I hope you can hear me.
Yeah, Divya, we can hear you well. Okay.
So, hi, I'm Divya Gopinath. Thank you, Karina, for that introduction into the work that we've been doing. I will be giving more details into a specific project that we've been working on, which is property inference for deep neural networks. So the key idea of this work is, given a trained DNN model, we aim to infer properties of that model as rules of the form pre implies post, where pre is a precondition characterizing inputs on which we expect the network to display similar behavior with respect to post, which is a desired output property, such as having the same prediction for a classifier network. The idea here is decomposition of a complex black box model into a set of rules aids in interpreting and understanding the model behavior better. So the properties that we extract are expressed as constraints in terms of the on-off activation patterns of the neurons of the network. For instance, for the rectified linear unit or the ReLU activation function, it is said to be on if the output of the node is greater than 0 and off if it is 0. So the key insight we had is, for piecewise linear activation functions such as ReLUs, they can be considered equivalent to conditional statements of traditional software programs. And hence, adopting a programmatic view of the DNN model, the logic of the network can be captured in the on-off activation patterns of the neurons. So the properties that we extract can be proved to be valid on the network using a decision procedure, which we tried to do so. And if not, on complex models, if it's difficult to obtain proofs using existing decision procedures, they can also be associated with a statistical metric of confidence, such as the number of inputs of number of instances satisfying these properties. So we basically extract two types of properties. So one is an input property which encodes predicates on the input space, which imply a certain output property. So here the precondition is a conjunction of constraints on all neurons starting from the first hidden layer until a certain intermediate layer or until the last layer. For instance, I shown an example here of an input property which states that for neurons in the second layer, if the neuron N20 is on and N21 is off and N22 is on, and the neurons in the third layer, N30 is on and N31 is off, then the network always predicts a label 0, that is the output variable Y0 is always greater than Y1. So this is an example of an input property that we can extract from a model. And such input properties trace convex regions of consistent labeling in the input space or represent inputs that are close to each other in the input space and on which the network can be proved to behave similarly. The other type of properties we extract are called layer properties, which group inputs based on some common characteristics at an intermediate layer. So basically, these are conjunction of on-off constraints on some or all of the neurons at an intermediate layer. As an example shown here, these could be constraints on just the neurons of the third layer, which imply that if N30 is off and N31 is on, then the output of the network is always going to be labeled 1. So the intent here is to capture properties based on semantic features that the network might have learned. So these are inputs which are not close to each other in the input space or don't look very much like each other, but they share a common feature which the network might have learned and uses to classify them. So we've employed these network properties that we extract to provide robustness guarantees, generate adversarial examples for proof decomposition, distillation, so on. But the focus of this particular talk is going to be how can we use these properties for explainability. So to start with, the properties that we extract, when expressed in terms of the input variables, themselves serve to explain the network's decision in terms of the characteristics of the input, and so they act as formal explanations. However, for perception networks, where the input variables are large and are typically raw pixels of an image, we try to make the explanations more understandable by applying visualization or attribution techniques along with these properties to determine, say, important features of the input images that might impact the network's decisions. For controller networks, on the other hand, where the input variables have more semantic meaning, such as they could be inputs to the controller algorithm, the properties expressed in terms of the input variables directly acts as specifications of the functionality or assumed guarantee type contracts for the model behavior. So here we present an example case study that we performed on the MNIST dataset, which is a benchmark for image classification networks. We used a model and extracted a number of input properties and layer properties on it. For every input property, we were able to actually precisely compute boxes in the input space or ranges of pixel values for which the network could be proved to give a certain classification. For example, I present here a visualization of images drawn from such boxes for input properties. So from this visualization, we were able to infer that the network gives the same decision to digits whose basic shape might be the same, despite the presence of some noise. On the other hand, with the help of layer properties, we were able to identify more semantic features. For instance, looking at images from the train set that satisfy the same layer properties, we were able to infer certain features. For instance, if we look at the group of fours which satisfy the same layer property, they might look different from each other as input images, but they all seem to have a certain common feature of the center line extending above the top of the digit, or all of them having a tilt towards the right. Similarly, for the group of zeros at the bottom, they all seem to share a common feature of a thick boundary. So by visually looking at these images, we were able to infer that these are probably features that the network has learned. And the benefit of this is this could probably help us assess the generalizability of the model to new inputs, which may not have been part of the train set. Also, this could help in debugging. For instance, if these were groups of images that were misclassified by the model, then identification of such a common semantic feature could actually point to the reason why these images were misclassified. We also performed a case study on a typical face recognition application on this data set called the labeled faces in the wild, which is again like a benchmark data set for evaluating face recognition networks. And we used a model which was trained using the faces of famous US presidents. And here, when we looked at images of which were satisfying the same layer property, we were able to find that the nose of all these images seems to have been the deciding factor in giving him, in assigning these images as belonging to Powell. Similarly, we found that nose seems to be the most important feature on Bush's face as well, which was determinant in classifying the image as being Bush. So what we speculate is identification of such a feature could also help us recognize or identify vulnerability in the network. For instance, one could imagine that just tampering the nose in an input image could change the classification that is, or the identification that was provided by the network. Moving on to a controller network, we performed a case study on the ACAS-XU application. ACAS-XU has a DNN model acting as a controller for unmanned aircrafts. Here, it takes in inputs which are sensory inputs, such as the range between the own ship and the intruder, the heading angle of the own ship and the intruder, so on, and provides horizontal movement advisories such as clear of conflict, strong left, weak left, so on, in order to avoid a collision between the own ship and the intruder. Here, the properties that we extracted acted as specifications of functionality for the model behavior. And here are examples of some of the properties that we extracted for clear of conflict, strong left, and again, clear of conflict. And these were specifications which we actually passed on to the domain experts. They validated that these were novel specifications which were not provided up front, and they also validated that these were supposed to hold true on the network model. But one could imagine that this could also help us identify behaviors which are unexpected of the model, and it could be used for improving the controller's performance or for debugging it. So this was a gist of the work that we did in property inference from deep neural networks. Thank you so much for this opportunity.
Thanks for having me here. In my part of the session, I will move to talking about some real world challenges in building, testing of AI and machine learning systems. I represent a team with an Infosys, which is a platforms and product team. It's called the Infosys NIA. And in Swahili, we say NIA means purposeful. So it's a purposeful AI platform. And the platform was designed really for benefit of people and businesses to make enterprise consumption of AI and ML very easily. So the whole idea is, while AI is an evolving area, but we also want the experience, the consumption experience for the businesses to be very, very easy, to have something which is an industrial grade AI and machine learning, and of course have a variety of ways in which you can, build, test, deploy, and host these. Now, within the space itself, obviously, when we began this, this was in 2014. We have collaborations today with Stanford, specifically the Stanford Dawn Group, which focuses quite a bit on democratization of AI, and we also work with UIUC on this space. So, if you look at the NIA platform itself, we have certain, as I said, foundational components. These foundational components include the natural language processing, ontologies, right? It's a lot of it is deep learning models. We have vision-based algorithms and so on. Today, specifically, all my use cases and challenges I will be speaking is in the space of documents, document processing per se, and how so that is going to be the area, primarily because if you look at organizations, we realize that 70% of the enterprise data today is in unstructured form, in form of documents, and being able to extract information from these documents is very, very critical step. So our entire focus is today, a lot of work we do within Infosys is in the document AI space. Here, I just want to give you a quick preview. Infosys NIA itself is obviously, while we use a lot of open source, we have quite a bit of patterns in the space. We have found ourselves in several analysts and analyst related discussion. But I think what is most important today in today's context is speaking about 3 important use cases, which I will double click and specifically talk about the challenge. The first of those is really related to one of the America's largest telecommunication company, which was interested in processing a lot of their lease contracts. So these lease contracts are tower lease contracts they take all over the United States. And these are 20 years old lease contracts. And they wanted to digitize these lease contracts, read the information in the lease contracts to see where the opportunities they can have for the purpose of revenue leak detection per se, right? So essentially, that was one of the cases wherein we read about 8 million documents, 20 years old, poor quality, scanned copies, and we were trying to read these legal documents, and they were not in the same language per se, right? Each of these contracts would differ in the way the content is written, because it would come from multiple parties, multiple landlords trying to lease their towers to this company. So the language of these the contracts differed quite a bit. Uh, and this was, in that sense, I could say, one of the largest machine learning projects, because we had to process about 8 million contracts in a matter of a month. So we had to actually go ahead, extract certain clauses. And in this particular case, we had a huge business benefit, because by reading these contracts, we could actually identify certain clauses. One of those clauses, for example, was related to rent reduction. So every time this tower lease is shared by another cell phone provider, uh, they would get 35% reduction in rent, which means if I can read these 8 million contracts and find out those contracts which have a rent reduction clause, and be able to get other statistics saying which are these towers which are shared by other cell phone providers, then you can actually find out and claim or ask for these rent reduction. Specifically, there was another clause which is related to capital expenditure. So if you look at a lot of these companies have capital expenditure towards hosting towers and tower leases. If you look at a games arena stadium, right, telecom communicator companies do contribute to the capital for the towers, and they are eligible for a refund So unlike, let's say, an airport wherein a telecommunication company puts in a lot of capital infrastructure which cannot be refunded, these games arena is seasonal, right? So they do get. So by reading these contracts accurately, the company could actually save about 90 million USD, right? So that's the first use case. The second use case is one of the big five technology companies. I can give you an example. Today, let's say you're using a phone. Uh, each of these phone may have about 1,500 parts, which could be sourced from different suppliers across the world. So it is just not the performance or the specification of these phones have to be met, but people are talking about safety, right, which is beyond lead, right? So when you have, uh, you know, these components being manufactured by different suppliers, they have to send a chemical report. So they literally crush. Let's say you have your phone is crushed. The chemical composition is sent to various laboratories across the world, and each of these laboratories actually send you what components it has, the cadmium, different kinds of composition. And the company actually has to disclose to IPC 1753. So it's a way in which these companies disclose. So the key challenge we had was when you get so many varieties of documents across the world, all of the formats are different, different languages. How can you have a machine learning algorithm which can understand these formats and extract the information and be able to sort of harmonize it in a standard way like IPC 1753? So that was an important thing where obviously we were able to, with time, improve the productivity quite a bit, right? Reduce the cycle time, which was otherwise being done manually with a lot of errors. So that's the second thing. The third thing which happened very recently is related to COVID, and SBA came up with this Paycheck Protection Program, wherein a lot of small and medium-sized enterprises within US who were affected by the COVID outbreak could apply for loans. So when you submit these loan documents, you submit your lot of IRS forms. So being able to read these documents, right, find out what information resides in them is also important. So due to the surge of volumes, we had a bank coming to us, and we could process about 15,000 loans in a matter of 2 days. So these are the three use cases. My plan is to actually talk about quickly about how our systems are designed. So today within the Doc AI, we have a design which we say mimics the way the human brain works, right? In terms of we have an engine which has multiple neural pathways. So we take a document, we look at the document from the sense of text and text place classification, right? Reading the different sections, understanding what it means. For example, you may read a contract to see, okay, is because of COVID, is there a force majeure clause I can look at? Right? So reading, understanding and classifying is one part. The second is, of course, you need to have the sequence and understand the context to it. So sequence to sequence kind of networks also we have, right? Third part is looking at it from the vision perspective, because a lot of information, vision-based algorithms provide orthogonal learning to what you learn from text, a completely different set of insights and inputs. So we have the vision-based algorithms. So we try to have an approach in most cases wherein we put them all together, and then we get much better and higher accuracy. So that's how the design of these systems are. Now, when we go for any real life applications of Doc AI, these are the three things which a customer really looks at. The first question is, what is the accuracy your systems can achieve? Second is how fast, both in terms of the response times of these systems, but also on the training time, right? How fast can you bring up these system and they can be up and running, right? That's the part. The third is it going to be cost effective, right? How much is it going to cost? So these are the three key expectations we see from the business side. Now, some of the practical challenges, again, I said my session is more or less going to be on the document and document related use cases. The first and foremost challenge which we face in any a kind of the system is the data preparation. Before even you go into data extraction, if you look at the content which we get, lot of times it's handwritten content. You have watermarks, blurred images. So being able to orientation correction, so being able to clear up these stuff and get it in a format that the systems can do extraction, right? That's very important. The second part is that, though these may be a lot of it, may be machine learning, but there may be certain pieces. For example, we always find OCR creates a lot of confusion on visually ambiguous letters and numbers. And any of these contracts or documents, what we are most interested in the numbers, right? We could be reading some payment information, we may be reading dates, times, all of these are numbers. So unlike a spelling correction where you can have a contextual, language model built to correct the spellings, being able to apply machine learning, because this is not even a learnable problem per se, right? So if a number one becomes an I or a dollar becomes an 8 because visually you cannot auto correct it. So what are the other ways of machine learning algorithms can be used, given that the straightforward spelling correction per se is not really relevant, right? Similarly, we also have other issues like, when you look at it, a lot of rich information. So if you have a 7.5%, let's say, increase in rent in a contract, that 7 1/2, which is a rich text with a certain property of a subscript, superscript, right? Or you may have some centimeter square of the material being tested, which is a mathematical representation, which is a rich text, but that gets converted to something very simplistic, like it could become a CM2, or the 7.5 could become 7 1 1 2, because you've lost the font related properties and so on. So those are a lot of issues related to that. The third kind of information which we always find is different, most often critical information lies in tables. So being able to identify tables, different kinds of tables, right? Border tables, borderlets tables, tables which span across pages, different kinds of orientation. So those are a very, very critical space. Alongside that, the language part. So we do have cases wherein it's just, even be it the voice recognition or be it these kinds of documents, it's never one language. Usually you have information present in multiple language, and that also uh, causes a lot of issues when you're dealing with the system, because even though you may be interested only in, let's say, extracting the English content, but still, if you do not understand what is there, these letters and characters of, let's say, in this case, a Japanese script could be converted or approximated to an English language, like, which will give you a lot of garbage. The last portion, of course, is, today in the document space, no document, is in isolation. Usually you'll have a hierarchy of these documents, and you'll have to know how they are related to, and being able to classify these documents without even having to digitally do them. Because when we are looking at it and trying to do classification, let's say, of images, right, we do a vision based. So the key question is, can we do a vision based classification for some of these documents and be able to create an hierarchy and link them, becomes very critical. Now, given these four challenges, I would actually, the good thing about my session is I'm just going to talk about problems and not the solution. One of the things, as I said, is, the telecom case, we had 8 million contracts, average of about 30 pages, and each document, because it's scanned copy, and we used to have images of towers, uh, land layouts there, we were about 3 MB, right? From these 8 million contracts, we landed up getting 2.4 billion paragraphs, right? And out of these 4 billion paragraphs, we roughly had about 30 intents. 30 intents per document means 30 paragraphs or 30 terms of importance. When I say 30 terms, one term could be a term related to contract preamble. Another intent could be related to rent, could be another preamble intent. The third one could be the termination clause, right, or the governing law. So these are the intents. So we had about 30 intent per document. And we also had to extract a lot of entities. So these entities are nothing but, you know, rent amount, percentage increase in rent, contract term, contract termination. So in all, we, if you look at these 88 million contracts, we had close to 24 million numeric entities to be extracted, which is rent amounts, percentage increase in rent, term, termination, and so on, right? Now, given the problems which I described above, uh, over 95% of the numerals were incorrectly recognized at the first time, right? So when we took these documents, processed them through an OCR tool, we realized every bit of it, right? About 65% of them had quality issues. And that's when we had to rely on certain ways. Here, of course, my session is not really going to talk about what did we do to handle the problem. But what I'm trying to say here is when you begin with a certain set of assumptions. But when you look at the data, we encounter problems and we try to keep iteratively adding newer pipelines, right, which is what is a pipeline jungle per se, to be able to do this. So this is one kind of issue. The second issue which I want to talk about, right, is in the same situation, right, where we had 8 million contracts. We had, since this is not a case wherein you can go to the open source, be it ImageNet or other sources to get training data. These were all related to lease contracts. So we had to we had to manually label them, and we had a team of lawyers who were actually labeling these data sets. We spent about 40K actually investing on these lawyers to train the machine, right? So we have a platform in which you can actually tag and create or label the data per se. And this was used to create ML. And finally, when the first time, the first iteration, when we built the ML model, we were shocked because after spending 2 months of effort and spending so much, we realized our accuracy was just about 54%. And what we realized was a very unexpected thing, that the most of the problems were because even though we had SMEs on board, right, 80% of the label data was incorrect. These were largely due to three reasons. The first reason was the lawyer's inability to know how to tag the data, inconsistency between the lawyers in the way they were tagging the data, and of course the third category was, the mistakes in them. But net this 18% of the label data was incorrect, which also brings us to a very important point about how do we ascertain whether the data which we take for labeling, right, is right. And this forms the foundation of being able to check the quality of the labels. The third use case, again, going back to the Big Five company, we had about 75,000 lab reports across the world, right? And these were obviously coming from different people, right? So the format, the language which is used, and not just the language, within English, the terms used to mean the same thing, right, were very different. Most of this information was in table and tabular data, and the tabular data also had a variety of variations. Right? So within the 75K report, we had 9,000 different variations. These variations meant different orientations of row columns. It meant different terms, right? The way they were using is all different, right? Again, there was a huge variance in the accuracy. So in certain cases, we were hitting a very low accuracy versus a certain cases where we were very, very high on the range. So then what we realized is that the documents, 20% of the documents which were in the low accuracy bucket had something in common, which was really about the multiple natural languages handling, right? The kind of mathematical symbols. So they use mu, sigma, beta, gamma, which were getting, sort of handling that was a problem. So this was the third challenge which I wanted to talk about. The fourth challenge again is, when we take these kinds of projects, right? In this particular case, I'm talking about SBA, PPA loan processing. We had about 15,000 loans, and each loan applicant would have 7 or 8 documents, which the person had to submit as a documentary evidence in order to be, eligible for this loan. Now, there was a huge variance, though a lot of these were, related to proofs about them filing tax returns, right? The number of employees they had, the wages of these employees, and so on. There was a lot of variations on how they had bundled it. Right? Many of them would actually join multiple years quarterly tax returns into one document, right? They had unnecessary documents which was not needed. They had provided a lot more than what was needed, and so on. So there was a huge variation, and what was needed is that in this kind of a case where it's very, very risky to completely automate the system, because these machines are taking decisions about who would be granted a loan or not, right? So what was very essential is that we had to really know what was the document, and also have identify these discrete documents properly. So if you have a bundle of documents, you need to break them up, even if the sequence is lost, into discrete documents. Classify the document level, not just based on the title, but even the page level you need to classify, and then you need to go ahead and extract, right? And make sure there are no duplicates and so on. So this is another thing wherein, we were having a lot of low accuracy in the first time when we did it, when we went with a title based classification and looking at only text and classifying. We were having a lot of miss, right? Which is when we had to go and change. So essentially what I'm trying to say is, when we try to meet these accuracy, I actually want to show you some of these samples so you can see what it looks like. This is the test report which I was talking about. If you look at it, right? 2 different languages, a lot of content is in tables. So if you do not handle the scripts of another language, even while you may be interested only in English, it could be a problem, right? And the same table within one report, right? If you see this page of the report versus this page, right? They're so different. The same thing is being presented. The other cases which I wanted to actually show is, if you look at this document, right? So you see it's tilted, right? There are a lot of black spots, scribbles written. So if you send this kind of document to an OCR tool, the tool will fail. So handling this was, very, very critical. See here, this is another document. So going back to what I was saying is that, while we did a lot of things, but we had to iteratively adopt many solution fallbacks. To begin with, we didn't guess, when we were in the test environment, we didn't think all kinds of combinations we would get in the production, right? So it had become, while we had beautiful self-contained packages, but we started writing a lot of code, right? And our pipeline itself for data prep became very, very complex. So we started handling the pipeline to have cleanup, slant correction, DPI enhancements, binarization. We added that to handle the numerals, because you cannot correct the numbers. So we took an approach of inverse text normalization, wherein we would look at the text close to a numeral. For example, if it says $3,000 only as text, and then you had the number, we would take the $3,000 only and convert it as a numeral and then check. So approaches of this kind, wherever it's applicable, so inverse text normalization. Third is handling different language packs, and also mathematical extraction. So this, to make sure all the rich text which we have, the information is not simply coded in, in certain, and loses information, but we kept the font and the font related properties. Methods for visualization, this was very helpful, specifically in the case wherein we had our SME teams and we found that there were a lot of errors. It was very important for us to go into and do this TSNE visualizations, which would tell us about the interclass conflicts and which were those classes which were not, which needed better disambiguation. Fourth is, of course, applying effectively a lot of our algorithms, not just the text, right? The parallel pathway wherein you apply a text algorithm, but you also have other ways of doing it so that, in essence, you have a higher probability of predicting things rightly. So this essentially is the summarization, meaning there is no one perfect approach. Based on the production data, we land up iteratively changing and adopting a lot of solution feedback, which makes the QA very, very difficult, right? Be it in the case of the telecom where we had millions of records to review, it's a nightmare. So it's no more that clear boundary like traditional systems where you clearly test, you have a QA, and then you roll it out in the production. This becomes a continuous stream. So that is what I want to summarize with by saying that, today it's become very, very complex. I do not think we have a great answer to this really in the practice side of things. Of course, one of the papers which really inspires is this paper written by a Google team on this hidden technical debt in machine learning. A lot of the concept they present seems to resonate very well in the practice. But again, what we have is a whole bunch of problems. And I would say in this journey of finding the ways to handle, we are possibly very, very early on. With this, I conclude my session.
Hello, everyone. This is Harleen. So what I'm going to talk about is how are we leveraging AI for building QA tools of future. So I think we heard a lot about AI, right from Dr. Jim, who very nicely put together the whole story, and then Karina, and then my colleague Rajeshwari. So what I'm going to conclude, I think is the last session, is about how are we bringing all these practices or techniques to build some of the QA tools. So I think we all appreciate this journey of QA, how far we have come. So when I started my career about 2 decades ago, it was mostly manual testing, right? And there were few scripts, maybe for regression, we used to automate. But where we are today, obviously those are things of past. Where we are today is the companies have started understanding, they have started appreciating, and in fact started using some of the AI techniques already in some form or shape, right? So they are using probably to optimize their scripts or maybe to predict some of these things. And the next level is where what companies are exploring, and so are we, is how do you bring some components of AI to make the entire automation smart? And how do you augment some of this AI with the traditional tools which have been using, probably which cannot automate a lot of stuff, right? So if I use UFT, Selenium, maybe I get a basic automation, but how do I add intelligence? And that's where a lot of companies are doing work and augmenting intelligence into those tools. And finally, where we are heading towards, so we have achieved 1, 2, 3, 4, and where we are heading towards is how can we make, beyond this, how can we make this whole testing as autonomous as possible? And which essentially means, just like humans, can I replace them with some of the bots who can come and do testing on behalf of me? So we are also in the early stages of experimentation in this area. So this is using some of the reinforcement deep learning methods, but this is where I think organizations want to go next after they have achieved AI-based test selection, smart automation, and so on. So what are when we speak about using AI in QA? So I'm talking in context of QA here. So what are the typical uses that we see, or when we talk to various clients, or when we are seeing in our projects? So there are a couple of things in which this is being used. So first one is what we call as data bots, right? So you do have your traditional ways of test data generation, but there are certain cases, there are certain elements where you cannot use the traditional tools. I'll give you an example. Maybe you want to take data from production, right? But you do not know what is a critical, even before you can mask, you do not know what are the critical data elements which needs to be masked. So in those cases, what we have used and what could come handy is, how can you do a pattern analysis for the data in production and then identify that these are the critical fields. Maybe you have two address field. One is of account holder and another is maybe the bank, but the other field, only one of the field is critical. So some of those techniques can augment your traditional data generation tools, and that is where the data bots come handy. Second use case that we have seen in practice is what we call as digital testers, right? So how can you have some of RPA or other AI models which could help the testers, right? When I'm doing my testing, how can it help me in some of the repetitive redundant tasks? Maybe it's a defect logging, maybe I'm downloading or uploading some of the data again and again. So how can some of these RPAs and RPA also have intelligence built in the latest versions of RPA tools, which they're calling as intelligent process automation. So how can we bring all those things together as digital tests? And third use case which we have seen, and this is one of the most common, is doing predictive analysis, right? So there is a lot of data that is available for QA teams. They can be in form of defects, they could be in form of production tickets, your application logs, or your execution history. So how can you apply? And that's the most common thing that we have seen in application, where all this kind of data is used and AI or machine learning methods are applied to give some of these predictions which can help the QA teams. And finally, what we have seen in usage is what we call as advisory bots. So these are the bots which help the testers, right? So maybe in traditional ways, you will have a dashboard which will give you a complete view after you're done testing or you are still doing testing. But the things have changed. Now what you want when I'm doing testing, I want real-time insights. And I don't even want to query or don't even want to go to that particular dashboard. So how can I have, and that's the practical use cases we have seen, where you build some interface, a conversational interface on your whatever dashboards or your reports, and they keep assisting in real time. They keep advising the testers in real time that this is what, critical things that you need to test, or this is how the release is going on, this is what the coverage is, and so on. So these are some very, I've tried to bucket them into common areas, what we have seen. Now, how do we build this, right? So I see that there is application maybe in certain places, or some people are trying to apply this into their organizations. So what is the whole framework that we have used? And Dr. Jim had spoken about the whole AI lifecycle, right? So this is something, the lifecycle which we refer to as for our framework. So this is about discovery, discover, learn, sense, and respond, right? So when, first of all, you need to discover the source of data. For example, on what do I need to build my ML or AI models on? So like I said earlier, this could be your defects, your tickets, codes, logs. So this could be anything on which you want to. Kishore, are you saying something? Am I audible?
Yeah, Harleen, we can hear you well.
Yeah, Harleen, you are.
Because I saw a notification that Kishore is speaking, so I thought maybe I was not audible and we're trying to say something. Okay. So yeah, so the first point here is, how do you discover the data? How do you identify the data on which you want to build your machine learning models? And then once you have identified the model, the data, underlying discovery of data has happened, then how do you train your models? And that's a learning phase. How do you train your models on that data, right? So I want to build certain kind of models on want to train them on a certain set of data. And once the models are trained enough, then they should have ability to sense, right? So they should be able to identify for what they have been built. Maybe they should be able to tell me that these are two correlated defects, or these are correlated areas based upon the way I have built the models. Or they should be able to tell me that these are the impacted scripts when something changes. So whatever that could be for which I have built the model, they should be able to sense and finally respond. So that is the most important feature, because it should have capability to automatically respond, trigger the response based upon whatever it has sensed. So it could be as simple as triggering some of the automated scripts whenever it sees some change. So essentially, this is the overall framework based upon which we have built our AI platform, which is our AI ML platform for testing. So using those principles of discover, sense, and respond. So this essentially gives a view of, so there are two things. One, what you will see is there are already some pre-built AI ML use cases, which could be used out of the box in the given situation. However, if those use cases cannot be used, it also provides the capabilities to onboard the custom use cases, which could be useful in particular context. So I will give you an example of some of the pre-built use cases that we have in this platform. So the first one is what we call as optimization. So this particular use case is based upon clustering techniques, which essentially means if you have a large repository of test cases built over a period of time, how it will be able to identify and remove the redundancies. What it means is it will be able to cluster similar test cases into a same bucket, right? So then the tester can take a call that whether I need to keep both or whether they are duplicate, or whether I can optimize my whole test suite based upon that. The second one, but we have seen what we have is on the prediction. So this is also very important use case in the way, because based upon your historical execution, there is an ability to predict the number of failures that you will have in the current release. So those influencing parameters could be anything, right? So they could be how many requirements, how many maybe change requests, or what was the size of the requirement which you were working, or even to the way like what kind of testers who are doing the testing, right? It's experience level of testing. So this actually gives a prediction on number of failures. Similarly, based upon the data that you have, maybe so the data pattern analysis could be applied in multiple ways. It could be, you are seeing the defects, right? So how are you seeing a correlation between various defects, and so that when I am doing my regression testing, I have a proper risk-based technique to identify the regression suite. And another use case which I will want to speak about is about the coverage. So this is, I think, one of the very important parameters for testers. We always want to know by end of our testing that, what is a code coverage, what is a functional coverage. So there are pre-built models here, which will give you both the code coverage after the execution is done, as well as a functional coverage. So functional coverage is with respect to your previous release. For example, in this release, these were all the functional flows which were covered, and it will draw a map and compare with the current release, and will tell you, what are the missing parts, what are the additional coverage that you have done, or whether it was identical to what you have done earlier. So all these, and there are a few other, right? For example, the reviewer, the test case reviewer, so which essentially is nothing but it is an automated way to make sure that the test cases that are being written are complete, non-ambiguous, and are meeting certain standards, right? And at the same time is giving the enough coverage with respect to the requirements. So these are some of the use cases, some of the pre-built use cases, and there are a couple of more, but I've just kept the list to a few of them. And like I said, that it may so be that tomorrow, if you want to use this platform, you may not want to use any of that, because the problem statement that you want to solve is completely different. And there is a capability where you can create your own models. They could be trained, they could be deployed on the same framework. And this particular platform has its own inbuilt visualization. At the same time, it can integrate with the CI/CD pipeline. So if you have any inbuilt CI/CD pipeline, it can also integrate with it, and it also integrates with a lot of third-party, standard tools. Now, given this in the background, I will probably take one scenario, one example on how we will use some of these use cases in a continuous testing scenario, right? So I've taken a very, very simple and simple illustration so that, we can appreciate how in the entire continuous testing lifecycle, some of these use cases will play a role. So let's say there's a user story, and the same user story is obviously being used by everybody in the team, whether it's a developer or tester. So developer writes a code, tester looks for to write the test scripts, and so on. Now, so there are various interventions. So if you look at this legend, this is what I will speak through. So each legend has a particular use case or particular capability associated with it. Right? So when a user story is created, the very first capability that we can use is a requirement reviewer itself. Right? At the very entry level, we can identify if the user story, if are there any ambiguities in the user story? Is the user story complete? Is the user story giving the message what it is supposed to give? Because if there are certain ambiguities at user story level, it is definitely going to lead to multiple other defects downstream. So that is one capability. Now after user story, based upon user story, there is a capability to automatically generate test cases and test scripts using certain NLP techniques. So that is another use case which I have demonstrated here. So automated capability using NLP for creation of test cases and test scripts. And similarly, like I explained in user stories, the reviewer, the same way there is an NLP based reviewer for the test cases as well. Now after that, let's assume that code is being checked in by the developer, and obviously now you need to add what are the test scripts which needs to be executed for the corresponding code. So there is an automated test script recommender which comes into play, and it looks into multiple. So this is the legend for it. So it looks into multiple dimensions, right? So it looks into your code changes. So which are the classes, which are the new code which has been checked in, and then traces which are the corresponding scripts which it should add into the CI/CD pipeline. It also looks at the execution history. Maybe there were certain scripts which were failing multiple times, and they are also related to this one, and it prioritizes and adds those scripts as well. It also brings the insights from your previous execution history, for example, from the defect patterns. Right? So if there was defects, too many defects in a particular application area, it probably will give a high probability and pick up those corresponding test scripts. Or it will also look at which of the application area, and if there was a correlation, which was again through defect pattern analysis, it will give certain correlation, and it will intelligently pick those scripts. And it will also look at what are the screen changes which has happened, and so on. So what I'm essentially trying to say, there are multiple dimensions which will be looked, and the corresponding test scripts will be picked up and added into the CI/CD pipeline. Now, when this execution is happening, so probably there could be a scenario where your UI of the application has changed. And typically, maybe those scripts will fail, and when the tester will analyze, he or she will have to analyze why the script failed. Was it because of the application failure, or was there an issue with the script? So in this case, there is a self-healing agent which will get kicked off in such a scenario. Let's say there was some change in UI elements. So it will intelligently diagnose those changes, and it will do the healing of those scripts. And hence your execution will continue, and you will see the results. So though it does a self-healing, at the end of certain cases, it may so be that probably the solution which was recommended here may not be the ideal one. So in your report, you would also see that which all places it has healed on its own, so that if there is a manual intervention which you need to take at the end of your execution, you can do that as well. So once this whole execution is complete, then obviously you want to know what was my code coverage, what was my functional coverage, what APIs were called, and then for the future releases, can I collect data for prediction and so on. And that is where this whole analytics dashboard, which will collect data from various sources, whatever is Jira, ALM, or whatever those sources could be, right? And it will give a code coverage. So we have integrated with some open source tool for code coverage. It will also provide the functional coverage and API coverage or any anomaly that it detects. So all these things could be visualized, could be used for the future release planning. At the same time, there is also inputs wherever we have access to production data. So we also take the insights there, but many places we have limitation of non-availability of production data as such, production systems as such. So then that step becomes optional. But in places where we are able to extract some of this mass data, that those insights also are taken from there. So this is essentially the overall summary of or I can say a day in a life, right? In a very simple way, how some of these capabilities can be used across a continuous testing scenario. Okay, and I don't want to spend time on this slide, but just to give you a summary of what I spoke, I've put a very simple 3 phases. Obviously, these are not 3 identical phases anymore in the agile and all, because everything happens at the same time. But what I essentially want to say here is, for your planning, execution, reporting, there are different scenarios which could be used. Even for example, the prediction statistics which are given, the prediction insights which are given, are very useful in the estimation process itself, right? Because it is able to tell you how many failures you can anticipate or how many defects you will anticipate. Based upon that, you can do your planning. Based on that, you can do your whole estimation or the resource onboarding. And another thing which I have probably not spoken about is about on this UI change analysis, right? So during execution, most of the time what happens is there might be a very minor change on the UI which might go so there was another thing which I spoke about, self-healing. But apart from that, visually, if you want to see that what has changed on the UI and whether everything is intact on the UI, and extremely important when you are doing digital kind of testing, right? So in the Go, it will check any change on the UI between 2 versions, and it can also notify those changes. To summarize what I've spoken, so this whole intelligence can be applied across testing lifecycle. So it helps anticipate likelihood and impact of incidents and defect through various methods like your defect diagnostic, anomaly detection, or code coverage analytics, etc. And it helps automate the test. It helps automate some of the activities which could not be automated earlier by traditional tools, and create really a zero time, zero touch kind of testing process. And finally, it helps to amplify the tester's capability. So obviously, if you give so much access to the data and so much access to the insights, so it really amplifies the tester capabilities to help him in the right decision making, which help him to do a scientific risk-based prioritization. It helps him to remove any redundancies, remove any waste in the whole process, and optimize and focus on what really needs to be tested and focus all the effort there. So some of these case studies or some of the places where we have applied some of these use cases. The first one is for a beverage company in US. So here the problem statement was on a large number of test suite which had built over a period of time. And here we applied this clustering mechanism to optimize the test suite, and it resulted in almost 20% of reduction in the whole cycle, because the number of test cases were reduced, right? Because many a times what happened in this case was there were multiple redundant test cases and they were executed every release, and this one-time exercise really helped them to reduce those 20% in per cycle. Second is from a financial institute in Australia. So here what was used was the defect analytic feature, which was able to identify and pinpoint the exact application hotspots so that the testing could be focused. And what we had seen as a result of that, there was approximately 30% of effort saving, because we were focusing on the right kind of testing and we were not just testing everything, right? And the next is for a cable broadband service provider in Europe. So here, what we used was a prediction method where it was able to predict the number of failures and hence the effectiveness, right? So like I said, so it will give you, because for example, if your prediction will predict that maybe in this release you will get 30 defects or 35 defects, or whatever that could be number, right? So beyond a point, if you are testing and you're not getting more than 30, 35, or you have got something close to that number, which means that you have uncovered most of the defects and you should be good to go. So that is a technique which was applied here for this particular project. And finally, for one of the publishing and financial information firm. So the problem statement here was, I think, typical, which many of you will be able to relate, is a UI test cases becomes very flaky from release on release, right? So from one release to another release, because of UI changes, your automation scripts start failing. So here we use the self-diagnostic and healing solution, the use case, the self-healing and self-diagnostic use case, through which we were able to reduce 40% of time it takes to really identify, debug, fix automation scripts and all, because the solution itself was able to identify automatically what is the issue, fix it. It was also able to tell that why this issue is it because of the UI change or is it because of data error, and to that level of details. So that is what it concludes on my presentation. So obviously with this various use cases or the various interventions from AI and ML, how you bring into QA. So there are way to improve effectiveness, efficiency, improve the productivity, and hence reduce the overall cost. So thanks. That brings me to the end of my presentation.
Thanks, Erleen, for sharing insights on the cutting-edge AI/ML-based tools that you have been working on and that make QA intelligent, predictive, and highly efficient. Thank you for that. Now I'd like to invite Venki, who is Global Head of Client Services at IVS, to give vote of thanks for the session.
Yeah, thanks, Viral. Thanks, Kishore. And before we do that, why don't we look at, if audience have any questions before we wrap it up?
Yeah, hi, this is Sugato here from California. I had a question, or basically a couple of questions. So I think from Professor Eric, I think we heard, Professor Jim Whitehead, I think we heard about the biases. So just wanted to understand how do we handle the bias in practical scenario. So just one example I was reading. So COVID, apparently the tweeters that are coming forth, half of them seem to be from bots. So this sort of like data correction, what could be a practicable way of handling these situations?
Right. Yeah, really great question. I think probably the first and foremost key is just understand all of the different frequency distributions inside your data set. So just make sure that when you have a data set that you look at for each of the major categories inside there, try to understand, okay, what is the frequency distribution across category A, across category B, across category C, and so on. So a lot of that is just kind of, making histograms or density charts, and then using that to understand what frequency distributions are there. If you notice that there is a bias, then hopefully there'll be an opportunity to go out and collect additional data. If not, then you can start using any one of a number of techniques for balancing your data set. So either reducing, classes that are overrepresented, or using synthetic data generation techniques to create more instances of the data categories that are poorly represented.
Thank you, Dr. Jim. You had one more question, or is that the only question?
No, yeah, so I had a question for Rajeshwari on the NIA platform. In fact, I was involved a couple of years back, but one of the missing pieces which clients used to ask was specific data-driven like benefit analysis. But then I think so in this case study, we saw that for some of the other applications, some very good data-driven benefit analysis. So I was checking for NIA, do we have something like that available currently?
Specifically data-driven analysis from the QA perspective, or how machine learning has benefited?
No, from NIA, yeah. So from NIA perspective, like given specific client implementations we have, do we have data to corroborate how it has actually benefited clients with quantitative insights?
Yes, certainly we do have that. We can share that. As I said, I think gone are the times when people are thinking this is going to remove humans, right? So that's no more the goal. Even in this contracts analysis system, it's really not a case we're trying to eliminate lawyers, not at all. What we're trying to do really is to, first of all, do things which human dread doing, which is to be able to read historic contracts of 20 years old, take them, digitize them, clean them up, extract the pieces of information and give it to a subject matter to look at it. So from that perspective, in this particular case, we had to read 8 million contracts to extract just the 4,000 contracts which had the clauses pertaining to capital refund, right? So imagine how the machine learning has actually created a sieve wherein so much of information has been and given precisely for the human, so that human can apply the decision on that. So I think we do have a lot of case studies, but we are clearly seeing a trend wherein machines are augmenting humans in the areas where humans do not want to do it, right? So we can definitely share that.
Okay, thank you.
I had a question for Dr. Corina. In terms of the explainability, is it one of the struggles that we have is one is, we want to understand how AI gives an output and, why is it giving an output? And the challenge is, if you try to peel the onion, it may result in things that, it cannot even explain, or it may not be very straightforward. It may be very convoluted. So is explainability is about, just at a broad level, giving at certain layers of deep learning some explanations, or can it actually describe the root causes of any particular information? For example, today if humans are making decisions to give a loan to a particular individual, we make that kind of a decision based on several data points which may be subjective as well as objective. Whereas when a machine makes the decision, it we expect it to be very objective, right? So where do you see the role of explainability? Is it only from an explainability perspective, or is it really about testing it perspective?
Hello, can you hear me?
Yes, we can.
Yeah, so
Yes, we can hear you.
there is a lot of research in explainable AI. So there are large projects and a lot of work. To answer you specifically, the machine is as good as the data set it learned from, yeah, and also so there might be errors and biases in the data set. So then a decision to give a loan might be biased because maybe the data set happens that maybe people with high income or a certain race or something get more loans historically. So this is one problem that you want to analyze. So this would be with bias analysis, and attribution techniques and also sensitivity analysis could also determine this kind of bias. So if you see that the decision of the network to give the loan depends more on a particular fields that is undesirable, then this explainability can help with that. Now, in our work, so because there is a lot of work, so there are many techniques that intuitively make sense, or maybe, so there are many techniques that, for example, highlight portions of images that lead to a decision. Divya showed something like that, and people struggle to align their understanding of the domain with what the network is doing. So there are many challenges in this respect. In our particular work, we think that because we come from formal methods, we think good explanations are in the form of rules that one can even prove or show with high confidence that holds. So we try to basically come up with rules over the input domain, or in this recent work that will appear at CVPR, over high-level features that are described as important by the human. So in your example, it would be certain fields in the input records that lead to the decision to take a loan or not. And then we try to derive logical rules over those input features. So for example, if the income is greater at certain value and the value of the discrete field like sex has a, let's say, male versus female, then the likelihood of giving the loan is high or something like that. So again, then in some sense, explainability is very much related to formal methods once you see it as a set of rules. These are more like insights. And I'm not sure, I hope it gives an indication of how these techniques can help in practical applications. So the machine is objective, but the data sets are subjective, and also the parameters are subjective. So there is a classical example where, you know, for an image data set, the network gives a certain class because there is a dot on the image or a copyright sign on the image that has nothing to do with the animal. So then you do need to really understand if the network gave the decisions correctly. Maybe it performs perfectly on your data set because all of the images happen to have that copyright sign for a certain class. But this doesn't give you confidence that you know, your network will perform well on images without that copyright sign. I hope.
Yeah, thank you, Dr. Corina.
Thank you.
Anybody else, any other questions, comments, feedback? Okay. Yeah, again, you know, one last question, Dr. Jim and Corina, you know, and Divya, you saw the practical world of the AI implementations from a document perspective from Raji, and you come from the research background and the academia background. What is your take on, you know, are there any solutions out there that could help in some of the things that Raji talked about?
I'll take a stab. You know, I was really impressed with you know, the progress that Raji was able to make. You know, I think she is attempting some of the hardest document understanding problems that I've heard of. So, so one perspective I have is it just feels like she's very much on the bleeding edge of, you know, what it is that people are able to do. And I think, you know, she very much hit upon what I think is one of the key problems there, which is kind of a lack of publicly available data sets for things like large corpuses of contracts or large corpuses of unusual tables, and especially that kind of multilingual tables that she was presenting. You know, so I guess, you know, what little I know about the particular problem, you know, comes from the related issue of trying to understand web pages, where you run into, you know, kind of all of the same problems except for the OCR, because, you know, you have at least access to a machine readable form of the information to begin with. But I think, you know, many of the same challenges are still there, you know, trying to understand tables, trying to, you know, kind of understand the, you know, the visual elements on the page, you know, which ones of them are, you know, part of the content, which ones of them are part of navigation, and so on. You know, I think you know, when I've seen other papers in the literature trying to tackle that problem, they use a similar kind of an approach, which is a pipeline where each stage in the pipeline tries to tackle a different part of the solution. But, you know, I think it's still pretty wide open. I don't think there's like a best practice or a like best understood way of approaching it. Anyway, Karina, maybe, or Divya, maybe you have some insight as well.
Yeah, I mean, I agree with you. We are actually in some sense fortunate because, I mean, I don't know, but in our applications for the controller part, the input domain is quite small. And in some sense, you can use a lot of domain knowledge because you know some physical laws. You know, there are certain constraints between speed. You know some the input domain maybe is well formed. Even if, let's say, an autonomous system is deployed in an uncertain environment, you still know something about it. I mean, I don't know. At least this is it looks like it for me. Maybe if I knew more about those documents, maybe there are some intrinsic laws that could help you there. Yeah, so I mean, on our side, we also like to think of hybrid models where you know something about the domain, and then you use that to, in some sense, structure your machine learning algorithm. So I think that, at least for autonomy, I think this is the way to go, or maybe where we want to engineer some properties into the machine learning that again come from the domain. But I mean, sometimes probably this would also help there. But yeah, I don't know enough. We have only looked a little bit at text processing. We looked at some sentiment networks. So this is the only thing remotely related. But again, in principle, I think a lot of the technology that comes from explainable AI should be applicable also to that domain. Maybe you will find, you know, ultimately some information that is statistically relevant or in some other ways. I don't know. Yeah, this is maybe.
Thank you.
Answer.
Yeah, you know, so I really want to thank, I mean, I think the primary objective of this virtual session was to sort of stimulate some conversation around, you know, even while developing a AI system, there is a tremendous amount of importance to be paid towards the quality of the system, you know, how the various techniques can be leveraged to really improve the quality of the machine learning system itself. And I think this was a fantastic session, and I want to thank all the speakers. Really appreciate everybody joining in, and thank you so much.
Thanks all for attending.